these kind of introductory words, and thank you all for coming. Thank you for the invitation to be here. This is a fantastic occasion. I'm very happy to see Vlad and Tristan. I don't know if Phil is joining us online. Yes, so I'm very honored to be here. So my talk will be about the topic that I've been interested in also jointly with Camillo, and which is also part of the theme of the special year this year at IAS. And it's also something very closely related to the work of Tristan, Phil, and Vlad, but it will be my own personal point of view of this topic. So I will leave some more things for Camillo to say about the work of the awardees. So synthetic turbulence is an expression that was coined by Greg Eying, I believe, and it just refers to something where usually if you're talking about partial differential equations, the equation gives you, its own properties, its solutions, and so somehow it has the upper hand. And synthetic turbulence and convex integration somehow turns the cards around. You play the equation. You're forcing the equation to admit certain solutions. And what I want to convince you is that this is actually an interesting game, also maybe from the applications point of view. So since the Clay Award is traditionally in Oxford, I think it's quite fitting to start with an Oxford quotation. This is by Cyril Hinshelwood, who got the Nobel Prize in Chemistry. There's several chemist Nobel Prizes in this particular subject, fluid mechanics. He said, fluid dynamicists are divided into hydraulic engineers who observe what could not be explained, and mathematicians who explain things that cannot be observed. Now, to be fair, he said this about 19th century fluid mechanics, but I think that quite a lot of what he said applies even to the 20th century and even the 21st century. And one of the challenges is just to close this gap between these two communities. So I want to give a couple of classical examples of this division between theory and observation. This is the most classical problem, I guess, in fluid mechanics, to calculate the drag force for the flow around the sphere. And this was already studied by Newton in his Principia in 1687, and he gave a formula that involves the density and the velocity of the fluid and the radius of the sphere. And this is actually a very quick proof in this book. It's basically just saying that if there is a formula based on these parameters, then it must be this one, just by dimensional analysis. A century later, D'Alembert also gave a formula, which is a famous formula called the D'Alembert paradox, which is very different from Newton's. F is equal to 0. So there's no force acting on the sphere. And almost 100 years later, Stokes revisited this and gave a formula that essentially agrees with D'Alembert's, but also applies to viscous flows. Now, the three formulas are very different. And what's interesting is that D'Alembert's and Stokes' formula is derived from the PD. They are derived from the equations of motion, but Newton's formula is not. And it looks very different. However, it turns out that all of them were right in a sense. In certain situations. So the situation, what situation they are correct and when they're not is determined by the Reynolds number. The Reynolds number is a dimensionless quantity that essentially describes how turbulent a flow is. And so it turns out that at small Reynolds number, if the flow is laminar, there's no turbulence, then essentially Stokes' formula is correct. Whereas for large Reynolds number, Newton's formula is essentially correct. And I just gave two pictures from the famous album of Van Dyck to demonstrate what is laminar and turbulent, although I expect that most of the audience, or at least a large part of the audience, is very familiar with this topic. So I just want to point out that this large Reynolds number regime is not actually something astronomically large. It's actually essentially an everyday, it arises in everyday situations, such as behind the golf ball or a car. So it's not really something out of the, very disjoint from everyday experience. The second example is even more everyday experience. This is the setup is that you have a flow coming out of a pipe with uniform velocity u, and there is a ball balanced on top of this on top of the setup. So I have this picture by my colleague Jonas Hirsch from Leipzig, who is one possible experimental setup. And another one, which is quite usual in sort of, so there's my daughter also a little bit in the background. You see these type of experiments. I think there's quite a few features of this type of video that would deserve careful study, but I just want to focus on the most basic feature, which is that the ball can actually be balanced, which means that the vertical position above the pipe is stable. Now, of course, this being a kind of very popular experiment, there is also a popular explanation for it involving the Bernoulli law, but I think that that explanation is essentially at the same level as the explanation using Bernoulli law that planes can fly. And the true explanation is much more complicated. So Landau so this is actually in the book of Landau-Lifshitz, looked at this particular setup, at least in a kind of idealized situation where the diameter of the pipe goes to 0, and studied the associated PDE, which is the stationary Navier-Stokes equations, and he calculated a precise formula for what is the velocity and what is the pressure distribution. It's of course it's rotationally symmetric, and this red curve is the pressure distribution at a certain distance above the pipe. And what you see is that it has a maximum exactly at the axis of symmetry, which contradicts the observation that this is a stable position. If this was the true pressure distribution, the ball would never stay there. Okay, so that's another example where theory and observation contradict each other. A third one, which already featured in last week's and 2 weeks ago in the Posttalk talks, and will feature also prominently in the work of Tristan, Phil, and Vlad, is what is known as anomalous dissipation. So in the Navier-Stokes equations, the energy dissipation rate, formally at least, is proportional to the viscosity, which is essentially, you can think of it as something reciprocal to the Reynolds number. So very turbulent flows would have, roughly speaking, very small viscosity in this formula. So the expectation would be, the naive expectation from the PDE is that as the Reynolds number goes to infinity, the energy dissipation rate should go to 0. But this is not what is observed. What is observed is that as the Reynolds number goes to infinity, the energy dissipation rate approaches a certain constant, up to some kind of accidents, which are even more complicated to explain. But it essentially stays above a certain positive value, and so that's that again seemingly contradicts this formula. Of course, not exactly, because you could have nu go to 0 and this gradient squared go to infinity. By the way, so this observation is in agreement with the Newton's formula in terms of dimensional analysis, much more than so it's okay. It agrees with Newton's formula. So these are 3 examples just to demonstrate that there is a big divide between PDE and what we can prove rigorously on the PDE and what we observe. That's why I think that Hinchelwood's quotation still applies today. Now, John von Neumann, when he was already at the Institute, I believe, wrote a fascinating article on the state of the art of turbulence. And this is one of my favorite quotations from that article. One has to talk not of one turbulent solution, but of many turbulent solutions. There is probably no such thing as a most favored or most relevant turbulent solution. So I would say that, at least for me, the message of Neumann is that the issue of uniqueness, one of the standard questions in PDE, is overrated. You should think about existence and other properties, but uniqueness is not really the correct question if you are speaking of turbulent flows. And of course, this leads one to think about weak solutions. Another, you might say, artifact of modern mathematics, but this is actually quite old. So let me just digress to say, what are weak solutions? Euler wrote down the Euler equations in 1757, and what they actually represent is just the continuum formulation of conservation of mass and conservation of momentum. And if you take a particular some subdomain of the domain where the fluid lives, V, and then integrate divergence, the second equation, you get this red formula, which basically just represents the fact that the same amount of mass is going out of that particular domain as what is coming in at any moment of time. The same way, this second formula represents that the amount of momentum leaving a certain domain is the same, which is the amount of momentum coming in. So again, so these are sort of, these red formulas are representations of conservation of mass and momentum, but there are no derivatives. So these red formulas, which you can also think of as a definition of a solution of the Euler equations, do not require any differentiability. Now, to be fair, this is not how Euler derived these, because Gauss actually was born 20 years later. Okay, so actually the wave equation was the first PDE ever written down, and already for the wave equation there was the question of weak solutions. So D'Alembert derived the formula of the general solution of the one-dimensional wave equation as a sum of two traveling waves. And of course, he claimed that, well, these f and g have to be twice differentiable, otherwise the equation doesn't make sense, and the physics doesn't make sense. And Euler, there was an interesting fight. I will mention some of this next week, some self-advertisement, between D'Alembert and Euler that went about for 20 years. Euler claimed that, well, but look, I take these non-differentiable solutions, non-differentiable functions f and g, and I still get a solution. So why is it not working? And it was essentially Lagrange who resolved this dispute between Euler and D'Alembert and came up with what we would call now the distributional formulation of the equation. And Leray did the analog for the Navier-Stokes equations. There's another way to think about non-differentiable solutions, which is by taking a Fourier series. And of course, this was introduced for the context of fluid dynamics by Onsager for the Euler equations. So, okay, so it does make sense to look at weak solutions. At least it's something historical from that perspective. Since Helmut said I look like a historian, I'm making these historical remarks. However, there's a problem because there are strange weak solutions. So this is a result of Scheffer from the early 1990s. There exist non-trivial weak solutions of the Euler equations with compact support in space-time. So these are solutions that are zero at a certain moment of time, then they're not zero at a later moment of time, and then they're again zero. So they contradict any sort of physical intuition about what the Euler equations should represent. And they also contradict the conservation of energy, which at least formally should follow from conservation of mass and momentum. It's even worse. Apparently in the class of weak solutions, there is no real evolution. So you can connect any initial velocity field and any final velocity field by a solution of the Euler equation. So there are infinitely many weak solutions that start at V0 and end at V1. Now you might say, okay, but this is the Euler equations. So, okay, in the words of Sasha Schnirelmann, the Euler equations represent a fluid that has been stripped of all its properties except the property to occupy space. So, but the same thing appears with the Navier-Stokes equations. Here is the famous result of Tristan and Vlad. There exist non-trivial weak solutions of the 3D Navier-Stokes equations with compact supporting type. So the same result as the Scheffer result for Euler. And also there's also no evolution. In the same way, you can connect any two velocity fields by a weak solution of the Navier-Stokes equations. So there's clearly something wrong with the notion of weak solutions. So to look at this question of what a weak solution, what properties it should have and what should be its definition, I want to talk about the question of stability and closure. And this is motivated by, at least my work is motivated by work of Tartar, who said that the only thing about turbulence that everybody agrees upon is created by oscillations in the velocity field. And I should say, he actually says, when I talk about oscillations, I actually mean oscillations and concentrations. So the classical closure problem in turbulence is you have a turbulent velocity field, and you think of that as the sum of a kind of average plus a fluctuation, where the average could be a long time average. This is what Reynolds introduced, or it could be an average over ensemble, which is the Kolmogorov point of view. And okay, so the question is, since this fluctuation is pretty wide and difficult to either measure or numerically simulate, what is important is to understand the average. And so the average will satisfy an equation. I've written it down for Euler, but you could do it for Navier-Stokes as well, which involves the terms of the Euler equations plus an extra term, which is called the Reynolds stress term, and it arises from the difficulty that taking product does not commute with taking averages. So it's the difference between the average of the product and the product of the average. Okay, and one can summarize the closure problem in this way. What is the equation for this R? We have too few equations here. There's an extra unknown that we have introduced. And the only thing you know about just from averaging is that this is a non-negative tensor, but that's all. Does it satisfy an evolution equation, or are there at least more constraints? Now, so the problem is that averaging is not really well defined. So one could consider weak convergence as a substitute for averaging. This has been in the context of fluid mechanics introduced by Perna Maida and then later Tartar in the context of wave equations by Peter Lacks. So instead of averaging, we think of a sequence of velocity fields. They could be solutions or approximate solutions, and they converge weakly, which means averages are converging. And so it's a similar type of decomposition. We have an average and a fluctuation, but nothing changes. It's the same problem that the operation of weak convergence does not converge with non-linearities. So it's the same issue about the question that we don't know what is the equation for R. However, now we have a very well defined mathematical framework. And in many cases, you can actually say something more than just abstract averaging. So in order to motivate this, let me digress and talk a bit about a classical problem in homogenization, what is called as the G-closure, question of G-closure. So here, think of the following problem. You have two metals with different conductivities, and you want to combine them in a certain way to end up with some metal alloy with some interesting property, like a different type of conductivity. So here, think of this particular example. The conductivity, this is a two-dimensional example, is given by these matrices. One is black and the other one white, and this is the sort of metal alloy two-dimensional domain. And so the question is, what are the properties of the equation when we have this kind of combination? And more precisely, we could think about repeating this pattern periodically, and then in the kind of weak limit, we have a sort of average. But the question is, what is the effective conductivity? It's not just simply the average of these two matrices. And moreover, it's not just that for this particular configuration, what is the effective conductivity? Can you characterize the whole set of all possible effective conductivities? Okay, that's the G-closure question. And so the question is really about replacing one particular equation, which has sort of pretty rough coefficients, by a whole family of equations. This makes the problem, originally it's a linear problem, now it's a nonlinear problem, but it's still easier to say something about it. So this is a classic. I just wrote this picture if you're familiar with how to compute the G-closure of this set. It's something that's, it's not even a sort of a one-dimensional set of conductivities. It's a two-dimensional set of conductivities, which is what I find interesting. So in particular, you can combine isotropic materials with isotropic conductivities and get something that's not isotropic. Okay, so now in fluids, the question could be formulated as follows. So this is a very rough, please excuse me, this is a very rough cartoon picture. Think of an initial data V0. And then, of course, classically, you might want to study, how does that, how is the evolution under say, the Euler equations or the Navier-Stokes equations. And just to keep something particular in mind, let's say that it's a sort of Kelvin-Helmholtz initial data, okay? It's unstable. So now take a small ball in L2 around this initial data and just try to understand how that whole ball deforms under the evolution. Now, the typical way to observe things is to take averages. So the natural observation, the natural thing in this picture would be to take the weak star closure of the image under the evolution of this ball. And then let the size, so instead of the typical thing, which is letting time go to infinity, let the size of this radius go to 0. Can we characterize the limit of this set as the radius goes to 0? And the problem is that in this particular case, it's known from experiment, but it's very difficult to prove anything, is that it's unstable. There are certain vortex structures created, even if the initial perturbation from the flat case, the flat Kelvin-Helmholtz interface is very small. So it's not really clear what to expect in this limit. But my point is that in this way, you again study a question about stability of the equation under weak convergence. Because what I want to understand is not what is this set, this intersection, but what is the equation that describes that set. Okay? Just like in the G-closure problem, it's not that we want to understand the set of solutions, we want to understand the set of equations that characterize this limiting process. And so this is sort of a way to study relaxation under weak convergence, and it's a kind of deterministic analog to study the question of what describes turbulence. So here there's a formal limit, of course, from the Navier-Stokes equations to Euler equations. This is what was studied by Onsager. The weak convergence limit was introduced by Dipenna and Maeda. And whatever way you do it, you end up with some kind of set of subsolutions where there's this Reynolds stress. And this is where convex integration comes in. There is a kind of new arrow connecting weak solutions of the Euler equations to this set of relaxations. It tells us that whatever limiting set of equations we got here, they actually correspond to true solutions of the Euler equations, even if it's only in a weak sense. Okay, so I want to. So this is a kind of meta theorem to explain what I was trying to draw in the previous slide. If you take sort of strict subsolutions, so that means solutions of this relaxed system, there is this Reynolds stress R, and strict means that now it should be strictly positive. We want to avoid the zero case. Then the sort of meta statement is that any strict subsolution can be weakly approximated by weak solutions of Hölder class with exponent 1/3 up to 1/3. So this is a big theorem that was motivated by the Onsager conjecture, and I'm sure Camilo will talk about that. So I don't want to talk about that anymore, but give some other examples of this principle of studying the stability of the equation or closure of the equation under weak convergence. Okay, so going back to the Navier-Stokes equations, let me just recall what Leray proved in his paper in 1934. So he proved the existence, global in time, of weak solutions, which he called turbulent solutions. And the method of proof relies on the following strategy, which is called compactness strategy. First of all, you look at what natural estimate you can derive from the equation, at least for smooth solutions. And in this case, it's the energy inequality, which is a little bit more than just saying that the kinetic energy, in fact, it's a lot more than just saying that the kinetic energy is decreasing in time, monotonic decreasing in time. It also includes the cumulative dissipation rate. And so this means that if you look at the set of solutions with, say, initial data bounded in L2, then this set of solutions will be in space-time bounded in these two spaces. They will be uniformly bounded in L2, uniformly bounded kinetic energy, and the cumulative dissipation rate will also be bounded. So L2 in time, H1 in space. So that's the first step of Leray's proof. The second step is to come up with a kind of approximation, regularize the equation because it's difficult to treat directly the nonlinearity, and show the existence of these approximate solutions, and then pass to the weak limit. We have a weak limit because we have boundedness in a certain Banach space, and since there is this bound in H1 and it embeds compactly in L2, that allows one to show that the weak limit of this quadratic nonlinearity is actually a V tensor V. So in other words, in this philosophy that I was presenting earlier, there is no Reynolds stress. Reynolds stress is zero in this particular situation. So the limit will be a solution. Now let's look at, in contrast with what Tristan and Vlad proved, it's non-uniqueness and let's say wild behavior. So wild behavior just refers to these weird statements like you can get from any velocity field to any other velocity field, all the kind of contradictory, seemingly contradictory statements. So we are talking again about the weak solutions of the Navier-Stokes equations, but now we don't have the energy bound. So the solution is actually bounded in the energy. So kinetic energy is again bounded, and one derivative is integrable. So it's in the Sobolev space W11, but in 3 dimensions, this does not embed into L2. So the upshot of that is that there is nothing preventing Reynolds stress to be generated in this weak limit process, as in the general case that I presented earlier. So, okay, so that's the difference. We're looking at a different class of solutions, and in this class of solutions, the equation is not stable under weak closure. And to see that in a sort of larger context, that paper generated a lot of activity in the field, and the various results exploring the bounds of the technique of their paper. One is that you can raise the power of the Laplacian, and if you do that, instead of looking at solutions with one derivative integrable, you're looking at 2 gamma minus 1 derivative being integrable. And you can check what is the critical embedding here, and it will be exactly if the power gamma is 5/4. So correspondingly, there's this the work of Luo and Titi. They show that the same result as one of Bookmaster Vico holds also for powers of gamma less than 5/4. And let me also mention, because they're both here in the special year, Alexei Cheskidov and different Luo, which is also a result of solutions of the Navier-Stokes equations in another space that does not embed into L2. Okay, so just to have a family of equations where you see this divide between compactness and wild behavior, you can look at the P-Laplacian. So here the viscous term is the P-Laplacian, or could be P-Laplacian type. And then what changes in the Leray framework is that the energy inequality now you have the Pth norm of the gradient. That's the only difference, and you can again check Leray's proof. The Sobolev embedding will be valid if P is bigger than 6/5. The embedding is compact, and correspondingly, Leray's proof via compactness works if P is bigger than 6/5. And the same wild behavior that Tristan and Vlad showed works if P is less than 6/5 for Leray-Hopf solutions. But now, because of this compactness, it fails. The equation stops being stable under weak convergence. My second example is the 2D vortex sheet problem. So if you remember the picture from my introduction, there is this uniform flow and then a sphere and then some sort of really turbulent behavior behind the sphere in this wake. And one classical way to study this that I think was introduced by Batchelor is by looking at a plane perpendicular to the direction of the flow and look at the divide between the laminar and the turbulent region, or laminar and another laminar region is the original one. So the picture is not completely correct for this particular argument, but let's say this is the curve, which is the boundary of the laminar region outside. And then a kind of model problem is to assume that we have a dynamics on this plane of this curve, where now the vorticity, the jump-in velocity, is concentrated on this curve. The vorticity is coming from the jump-in velocity, and then you can write down a well-defined evolution equation for this problem, because you can so from the curve, from the shape of the curve and the vorticity strength on the curve, you can calculate the velocity. And so here is the, oops, I think I'm jumping ahead of myself. Okay, so that's a Biot-Savart law, just how to calculate the velocity. So this is the initial configuration where the vorticity is just concentrated on this curve. And Leray's strategy, the compactness strategy, was implemented by Delors in 1991. Global weak solutions proved the existence of global weak solutions, provided that the initial vorticity density is positive. And so the strategy involved, again, starting with a kind of a priori estimate, an estimate that is true for smooth solutions. And because of the vorticity equation, the total mass of vorticity is preserved. And so that gives an a priori bound. And then passing to the limit, I'm skipping the step, which is the approximation. Passing to the limit involves basically showing that under these conditions, the divergence is 0 and the rotation, the curl is given by a positive measure, then there are weakly continuous quantities. And this was the realization of this is an aspect of, it's called compensated compactness. And in terms of the framework I was sketching earlier, this means that in passing to the weak limit in the nonlinear term, there is a Reynolds stress, but it's a multiple of the identity. And so being a multiple of the identity means that you can put it on the pressure term. And so even though we don't have strong convergence of the velocity fields in this weak limit, the equation is still stable under weak convergence. Now there is another way of studying this problem. As I said earlier, you can calculate from the vorticity, you can calculate the velocity, and if you assume that the vorticity remains concentrated on a curve, then you can calculate an expression for how the curve should evolve under this evolution. This is called the Birkhoff-Roth equation. And the problem is that although this is locally well posed for analytic data, it's ill-posed essentially for all non-analytic data. And the reason is that small perturbations end up being very large in time. Now, so these two approaches to defining what is a solution, each one has its advantages and its disadvantages. The advantage of Delors' approach is that you have a global existence for a large class of initial data. But the disadvantage is that you don't actually know anything about the structure of these solutions. It's just an abstract existence result. The advantage of this one is that you see exactly what is happening with the solution under the evolution, but it's basically ill-posed. It's difficult to show even existence for a large class of initial data. So an approach which is somehow in between the two follows from these ideas that I presented earlier. And this is work with Fran Mengual, who is also here, and he talked about this last week in his short postdoc talk. Let me just recall the basic idea. So we can prove the existence and the non-uniqueness of weak solutions, which are energy is decreasing, and so the vortex sheet, the initial data is a vortex sheet, but it can have a changing sign. And so the idea is that we make a following ansatz. For positive time, there is that the initial vortex sheet is evolving in time, but it's also opening up. So there's a kind of tubular neighborhood or turbulence zone around this curve that is opening up. And okay, so this is maybe video, yes. So you see that the curve itself, the mid curve, this would be the evolving of the initial vortex sheet. This is moving in time, and it's also opening up into a region. Inside this region, we only have a weak solution, and outside the region, the solution is still analytic. There's no vorticity. So the vorticity is spreading inside this region. And the way to think about this type of construction is that we actually just need to construct the subsolution. So we need to construct this Reynolds stress, and so it's not so good to think about the closure problem. What would be the equation of R? It's better to think of it as a control parameter. You're trying to maximize something or minimize something. The same way as the effective conductivity is something that an engineer would think of as a control parameter. And with this geometric ansatz, that control parameter can be thought of as a way, I mean, kind of geometric control. We just want to, so given the shape of the turbulence zone, which is determined by the evolution of the mid curve and the size of the growth of it, that determines R by just solving a boundary value problem. And if we optimize over all possible shapes of this turbulent zone to achieve maximal dissipation rate, then we get something that at least to the naked eye looks like it's enclosing the possible growth of vortices coming from perturbations of the flat sheet. So let me just say, so here we are taking not a mathematician's approach, but more an engineering approach where the benchmark is given by the picture should look nice. Correct. It's not much more than that. We are constructing solutions, but okay. That's all. So the third example is concerning the MHD equations, 3 dimensions. So just to say what it is, you have the Euler equations coupled with the Lorentz force. So there's a magnetic field B. The magnetic field is solving the Faraday Maxwell equations with Ohm's law. So the electric field is given by the cross product of the magnetic and the velocity field. And this system of equations has a large, a very rich structure. The total kinetic energy is, the total energy is conserved, just like for the Euler equations, but there are 2 more conserved quantities known as cross helicity and magnetic helicity. And so of course, there are, analogously to what happens in the Euler equations, there are criteria on regularity of the solution, which lead to conservation of total energy, cross helicity, and magnetic helicity. But it turns out that this the magnetic helicity has a very special properties that is somehow more subtle than the other 2. So I want to talk about this a bit. Okay, so what is the physical significance, or what kind of phenomena one is aiming at? Well, if you so in reality there should be some viscosity and some magnetic resistivity in the system, but what is known from observations is that in a kind of turbulent regime where both of these parameters are small, there are kind of 2 time scales. There's a short time scale over which the kinetic energy is dissipating, so the fluid, the plasma, comes to rest more or less. But on a much larger time scale, the magnetic field also comes to a certain rest, but not to 0, but to some kind of steady state. The steady state would be the global minimum of magnetic energy subject to the given helicity. And so this is something that's this question is important. There's a NASA project studying how this can happen by kind of vortex reconnection, magnetic field reconnections. It's important to understand this because of solar flares, the speed of energy dissipation in solar flares, and mathematically, what is complicated is that if V goes to 0 first, then there is nothing that the magnetic field can do other than just also put to 0. So this reduces to the heat equation, but this is not what is observed. So this system, at least part of this system, has a special structure in terms of the PDE. The Faraday system is a standard example of what is known as the diff-curl lemma, which basically means that the product of E times B, the scalar product of E times B, is a weakly continuous quantity under certain conditions. And this is important because this is exactly what determines the evolution of magnetic helicity. And so, using this structure, Lindbergh, Danny Faraco will also join the special year in January, showed that if nu and eta go to 0, consider the limit of Leray solutions of the MHD system, then magnetic helicity remains a conserved quantity. And so somehow we need a notion of weak solution that has these two aspects. On the one hand, it is supposed to conserve magnetic helicity, because that's what observations tell us. And on the other hand, it should have anomalous dissipation of total energy and cross helicity. There are these two requirements from observation. And so that's where weak solutions come in. And there are two recent results. One is by Beakey, Tristan, and Blood, who show the existence and non-uniqueness of weak solutions which do not conserve the energy and cross helicity, but they also do not conserve magnetic helicity. And with Faraco-Lindbergh, we showed that in a different class, you can find solutions that actually conserve magnetic helicity, whereas they do not conserve energy and cross helicity. And so the difference in the two results is the integrability in space. This is in L2, this is in L infinity. And it is known, I don't want to go into the details, that in this class, a fortiori, magnetic helicity has to be conserved. Let me just say what is the basic idea that ties in with what I was trying to explain in the general framework. It's the question of stability of the equations under the conditions of what type of solutions you're looking for. Solutions which are L2 integrable or solutions which are bounded. And if you're looking for bounded solutions, the Tartar-Murat diff-curl lemma, which was 2 slides before, will tell you that there is a certain special structure in the Faraday system, which is this one coupled with this one. So this is the Faraday system. In the MHD equations, the electric field is a cross product of magnetic field and the velocity field. That doesn't have to be preserved. It's again a kind of it's nonlinear. It's a product of two functions, just like V tensor V in the hydrodynamic case here. So if you have the hydrodynamic part of the relaxation, there's a Reynolds stress term. But this one, there's a ghost remaining in the weak limit, namely that the magnetic field and the electric field have to remain perpendicular to each other. And so this is, let's say, the main observation. And if you look at this relaxation and then use a kind of meta theorem like the one I mentioned in the context of the Euler equations, that leads to this type of result. Okay, so that's it from me. Thank you for your attention and congratulations.
Thank you, László, for a beautiful lecture. We don't have the capacity to take questions from our online audience. Is anybody in the room who would like to ask a question?
Well, I'm interested if you could say a few more words about what it might mean for physics, for fluids. If in some sense this solution is non-unique, does it mean that in principle some data at the atomic level is needed to pick the right solution?
Yeah, of course, that's a good question. I would say it's maybe it relates to this cartoon picture that I was trying to show. You see, if you expect, or if you believe that in this limit, if rho goes to 0, you don't get a single solution. Let's say even V0 has a well-defined trajectory to Vt. But if you make small variations of V0, it's unstable, and the set somehow, I'm not very good at drawing this, but it will be very large, the set after time t. And even as rho goes to 0, that set will not shrink to a single point. So this non-uniqueness is supposed to represent that set. So it's kind of like the high frequency limit of taking perturbations and then looking at the evolution. That's how I would think about this. It's not that that particular initial data has more than one solution. It's that it's so unstable that if you're not completely sure about what the initial data was, you will see a whole bunch of possible realizations.
But then should that be described, probabilistically or stochastically somehow?
You could do. I mean, that's of course you can instead of a set, you can take a measure and look at the evolution of that measure. But I don't think that the picture would be very different. I mean, this is why I wanted to cite Neumann, because if you introduce a probability measure, you have to. I mean, you start to think about what is the most preferred solution. I'm not sure that's a good way to think about it.
So 2 questions, just kind of following up on this. I mean, but could you think about it in the sense of in the same sense we think about there being a non-unique characteristic, for Lagrangian particle motion connecting something, that being a source of dissipation. It'd be fine if there were many non-unique, I mean, if there were non-uniqueness coming all together and that was somehow some idea of dissipation, right? Does that fit into the way you think about this? That's kind of maybe what Tom, I don't want to put words in Tom's mouth.
Non-uniqueness of Lagrangian.
I mean, in the sense, that's what stochasticity gives you, right? It means that there are many paths that could have brought you here, and then you get some averaging over that. That's kind of a loss of information. So in the same way, if there's if there's many paths that could take you forward here, that would be a source of dissipation, except at a kind of a higher level in a way.
Yeah, I think you could think of it that way. Or I mean, you can also formulate the Euler equations as a variational problem in a Lagrangian setting, and that's a highly non-convex. So I don't know what would be, what happens if there's many ways you could realize a minimum for the displacement problem, and take some kind of average of that.
Is there something why did you go to MHD? Is there something extra degree of freedom there that's useful in some sense, or is it?
Well, it's kind of this, it has both these features. It is stable to a certain extent, but not completely stable. So it has the stability of magnetic helicity, but the same kind of anomalous dissipation of energy. That's why I thought it's a nice example.
Anything else? Well, let's thank László again for a beautiful lecture.